All right, everyone. Welcome to lesson 20 of the semester. And lesson 20 will be all about the limit comparison test. Before we get started with the math, though, so some of you may have noticed that assignment 11 is a bit different because it doesn't have the word Chronos in front of it. And that's because it's not a Chronos assignment, it's a Canvas assignment. Unfortunately, we couldn't get the Chronos built for that soon enough for it to be relevant in class. Like you would have had that homework next week or something, like way after it would have been relevant. So we just made that one a Canvas assignment, but the ones after that should be Chronos homeworks. One main difference is that with that, since it's a quiz, it's technically a Canvas quiz, but you have unlimited attempts. You need to enter in all of your answers at once. So if you decide to come back later, I would recommend writing down the answers that you got so far. So you don't have to just redo all of the questions. So I apologize for that. But you do have unlimited attempts to do them though. Are you pretty sure it saves it? Oh, okay. Well, just in case, I might write them down. You can't submit. Yeah, you definitely can't submit one question at a time. That's for sure. All right, anyway, so that's different. That'll just be only assignment 11 though. The rest of them, like 12, 13 and beyond, those should all be Chronos assignments. All right, let's go ahead and talk about the limit comparison test. So as a recap from last class, where we learned about the direct comparison test, the direct comparison test enabled us to take a series that we were interested in and find a series that looks similar, but is easier to analyze. So usually kind of chopping out some unnecessary terms. So depending on what that comparison series did, our own series that we care about ended up usually doing the same thing. But one problem with that is in order to use the direct comparison test, we needed to have the inequalities go in a certain direction. But unfortunately, the signs weren't always with us in that. So sometimes we couldn't get the inequality to go the right way. So what we're going to do today is we're going to learn an alternative to the direct comparison test called the limit comparison test, where it's not essential that one function be bigger than the other for the entirety of of all the n values. All right, so let's talk about what the limit comparison test is before we start using it. And again, 3 words is too many. So this is going to be called LCT. All right, so suppose we have 2 positive sequences, AN and BN. So this is the same restriction that we had before. I guess instead of positive, I really should say non-negative. They could be 0 sometimes. That's not a huge issue. We have 2 non-negative sequences, AN and BN. And we want to know about the convergence of A, which is the series for AN, and B, which is the series for BN. So just like last time, AN is going to be our original series. That's the one that's given to us. And then this one is going to be the comparison, or the one that kind of looks similar to our original one, but is a bit simpler. Okay, so what we do is we compute the limit L, which is the limit as n goes to infinity of AN divided by BN. So what this limit is doing is it's computing the relative size of these lists of numbers as we go along. Now, depending on what this limit is, we can conclude 3 different things. So if the limit is anywhere from 0 to infinity, then A and B do the same thing. Same thing as in one word. And by that, I mean both series converge or both diverge. So if we get something in between 0 and infinity, then they're both going to do the same thing. And this is usually the most desirable outcome. What about if we end up getting 0 for this? If we end up getting 0 for this and B converges, then A converges. But if we get a limit of 0 and we have B diverging, then we don't really know if A is going to diverge. So this is kind of like so this situation is smiley face. This situation is like slanty face. And then here, if we get a limit of infinity and B diverges, then A diverges. All right, so this one includes infinity. So if we get an infinite limit, if this limit goes off to infinity and Bn is going to diverge, then and B is going to diverge, then A does. But if B converges and we get infinity, then we don't really know. So that will also be a slanty face. All right, so let's see why this works. So why can we just have this as a limit and then they end up doing the same thing? Well, let's say we end up getting this limit being 2. Like let's just say hypothetically L is 2. Then that means that in the long run, the numbers in the AN list will be twice the size of the ones in the BN list. Now, if the BN ones converge, then the series for AN is probably going to converge to something. It's just going to be twice as big. But if BN is going to diverge, like go off to infinity, then AN will probably diverge as well because it's going to go to 2 times infinity, which is still infinity. So if we get L being something in between 0 and infinity, it just means that effectively, in the long run, one of these lists of numbers can be thought of as a multiple of the list of other numbers, meaning that they do the same thing. Now, if we get 0 here, let's say we get 0 for this limit. So that means that AN is going to be really tiny compared to BN, right? Now, if BN is converging, but A is going to be even tinier than it, well, then A is definitely got to converge as well. So that's kind of similar reasoning to what we had before. So if this limit's going to 0, that means AN is going to be a lot smaller in the long run than BN. And this final situation is the reverse reasoning of that. So if we end up getting infinity, that means that AN is going to be much bigger than BN in the long run. And if B was a series that already was diverging, and we add up the numbers for AN, well, that's going to add up to be even larger than before. So usually we want to get this situation here, but if we want to show convergence, this is okay. And if we want to show divergence, then this is okay. But we can't show divergence with this or convergence with this. All right, so enough about that. Let's actually go ahead and use the test and you'll see what I mean. Okay, so use the limit comparison test on the series n equals 1 to infinity of n plus 1 divided by n cubed minus n plus 1. So this right here is our AN, and this whole series is our A. Now, we need to pick just like the regular comparison test, we need to pick a comparison series to compare it to. And usually the comparison series is we pick it in the same way that we did for the direct comparison test. Wait a minute, am I recording this? Uh-oh. Yikes. Okay, let me start recording. Oh, I am recording this? Okay, good. Oh, yes, I see the little thing there. Oh, I freaked out for a second. I forgot that I did that. All right, anyways. So when we pick our comparison test, that's going to be the same. We're going to pick that in the same way that we did for direct comparison. So how do we do that before? Well, we pick the dominant term on the top, which is n in this case, and we pick the dominant term on the bottom, which is n cubed, and we just use this over this. So our Bn for this problem is going to be 1 over n squared if we simplify that down a bit. All right. Oh, that'd be even worse. Yeah, if I just stop recording right now. Yeah, then I'd miss the whole class. So my B series is the sum from 1 to infinity of 1 over n squared. And this is something we've seen quite a bit at this point. What is this going to do as a series? It's going to converge by the p-test, right? Okay. Now, so far, this is the exact same thing we've done with direct comparison, but here's where they're going to be different. Now I'm going to compute my limit L, which is the limit as n goes to infinity of an. So we have n plus 1 over n cubed minus n plus 1. And all of that will be divided by 1 over n squared. All right, well, dividing by a fraction is the same thing as multiplying by the reciprocal of the fraction. So we have n plus 1 times n squared over 1. And then we have n cubed minus n plus 1. All right. So if we keep going with this limit here, we multiply by n squared. That's n cubed plus n squared over n cubed minus n plus 1. All right, so now let's go ahead and take this limit. What do you guys think this limit is going to go to? Anyone know? Yeah, it's going to go to 1, right? And how did we know that so fast? Well, the degree of the top and bottom are the same. They're both 3 n cubed. And so we look at the leading coefficients. Well, we really didn't have any, so we can just assume those are 1. So we end up getting 1 for this limit here. Now, if you didn't realize that, well, I would definitely encourage you to understand how rational functions work with limits. That's something we're going to be seeing a lot. But even if we didn't, we could have technically used L'Hopital's rule here as well. All right, so we get 1 for this. So what does that mean? That means we're in between 0 and infinity, and we're in smiley face territory. So that means that A and B do the same thing. So since B converged, that means that A will converge as well. So since 0 is less than 1 is less than infinity, and B converges, then our original series converges too. Converges, and we would say by the LCT, or limit comparison test. Can the LCT be used in lieu of the direct comparison test? Yes, it can, and my bias is to use the limit comparison test as often as possible. I personally don't really like the direct comparison test very much, so by default I use the limit comparison test. But we'll see later that the limit comparison test does have its limits. I guess you could say. All right. So with that example done, let's do a similar one. Only you guys will lead the way this time. Determine if the sum of arctan of n over the square root of n minus 1, starting from n equals 2 and going to infinity. I know it says 1 in the notes, but that's a mistake. Converges or diverges. All right. Why don't you guys take a look at that one? Now, I think it's clear to what you should pick for your BN on the bottom, but on the top, this is kind of similar to that sine example we had last class. Think about what arctan is bounded by. Is it pi over 2? It sure is. Is the denominator 1 for Bn because it can't be less than 1? No, the dominant term down there is root n. So I would pick root n for your bottom. Yeah, you can think of it that way, Cole. That's fine. You kind of just chop off the lower powered stuff. So we don't really need that -1 down there. That's going to be nothing compared to the n. So we just get rid of it. Logan, you got divergence? We'll see. We shall see. I mean, it's a 50% chance you just guess. So, in fact, some of these homeworks you can do without really understanding. So you can just randomly pick between converges, diverges, but I wouldn't recommend doing that. Yeah, it's supposed to be n equals 2. It's not. Yeah, n equals 1 was a mistake for obvious reasons. Give you guys another minute or so. Think about this. We get 2 tries per question. Funny. Wasn't a joke. All righty, let's take a look at this. So we need to find a suitable Bn for this. So let's see here. Now in the long run, what's arctan going to do? Well, in case you aren't familiar with it, the graph of arctan looks something like this, where it has these asymptotes at pi/2 and -pi/2. So what's arctangent going to do in the long run? Well, it's going to head towards pi/2. So eventually that's going to act just a whole lot like pi/2. Now in the bottom, the dominant term down here, since we have more than 1, will just be square root of n. So this is going to be my Bn right here. All right, now let's take a look at what Bn does as a series. Excuse me. All right, well, we can move out the pi/2 because that's just a constant. And then we have our sum of 1/√n. All right, how did I come up with Bn again? I looked to see what arctan does in the long run, and eventually arctan is going to be very similar to pi/2. So that inspired me to simplify it by just picking the constant pi/2. And then the bottom, I have these 2 terms here, but n is going to be the more powerful one. So I keep that. All right. And then now what is Bn going to do as a series? Is this going to converge or is this going to diverge? It's going to diverge. That's right. It diverges by the p-test. And how do we use the p-test here? Remember that the square root of n is actually n to the 1/2. And 1/2 is indeed less than 1, so it's going to diverge by the p-test. So that leads us to believe that our original series will probably diverge as well. So let's take a look at the limit. So we have the limit as n goes to infinity of an, so arctan of n over root n minus 1, divided by bn. Now, henceforth, I'm just going to flip the fractions over by default. So we end up getting this right here. Because most series come in the form of fractions. So that's what it's always going to end up being, reciprocal at the bottom. All right. Now, what I'm going to do is I'm going to group this limit together in a different way. I'm going to have root n over root n minus 1 times arctan of n over pi over 2. All right. So did I just use the direct comparison test? No, remember, these are totally separate here. So I don't need to verify if something's bigger than the other here. All I need to, but I do, the one thing it has in common is that I do need to find something that's similar, the bn. So the thing they have in common is finding the bn. The different part is, rather than doing an inequality, I'm doing this limit instead. You don't have to do this limit for the DCT. All right, now let's see here. We have an n to the 1/2 power up here, and our dominant term down here is also n to the 1/2. So this limit's going to end up being 1. So we have 1 for the first limit. And then what do you guys think about the next part? Arctan of n over pi over 2. What's that limit going to be? That's going to be 1 as well. That's right, because arctangent heads to pi over 2. So we're going to have the same number divided by itself. So once again, we get 1 for the limit right here. Now remember, it doesn't need to be 1 specifically. All it needs to be is between 0 and infinity. All right, so now we can make our conclusion. So since the sum from n equals 2 to infinity of this diverged, not diverged, diverged by the p-test, our original series diverges by the limit comparison test right here. Where did the first one come from? It came from us having a root n up top, and then the dominant term down here was also a root n right here. So that's how we got 1 for this. And then arctangent heads to pi over 2 as n goes to infinity. So then those are going to be the same. What does the limit of 1 mean? It doesn't necessarily need to be 1. It just needs to be between 0 and infinity. And 1 is indeed between 0 and infinity. So if we get a limit like that, what happens then? Then the series do the same thing. So since B diverged as a series, then that means that A is going to diverge as a series. So we have to pick a certain number for Bn. There are honestly multiple Bn's that work. So rather than picking pi over 2 over root n, we could have just picked 1 over root n. That would have worked just as well, although our limit would have been a bit different. It would have been 2 over pi. But that's still between 0 and infinity, so it wouldn't really matter. So there often are multiple choices for Bn. And that's one thing we need to keep in mind later. So I'm glad you asked that question. All right, let's do another example. Example 2. So determine if this series converges. 2 to the n plus n squared over 3 to the n minus 1. All right. So just because the limit converges, doesn't that mean the sequence converges? Well, if the sequence that we're adding up doesn't converge, like if we knew that this sequence didn't converge right here, then we could immediately say the series would diverge by the test for divergence. Because if this diverges, it's certainly not going to head to 0. That would be that situation. All right. So let's take a look at this guy. So I want to use limit comparison here. So I need to pick my Bn. Now let's see what the dominant terms are on the top and bottom. So I have 2 to the n plus n squared. Which of these is going to be more powerful in the long run? It's 2 to the n, right? The exponential function. All right. And then between 3 to the n and 1, it's going to be 3 to the n. So that kind of suggests that our b sub n should be 2/3 to the n. That sounds like a good choice here. All right. So then let's look at the series, the sum from 2 to infinity of 2/3 to the n. So what do you guys think this is going to do as a series? 2/3 to the n. Yeah, it's going to end up converging. That's right. And how does this converge? Well, this is a geometric series. And 2/3 is less than 1. So these numbers are getting exponentially smaller as we go along. So when we add them up, it'll add up to something nice. In fact, this is one of the rare series that we can find the sum of using techniques from a few classes ago. We could use the formula to find out what this is going to sum up to. All right, so since our B is going to converge, that leads us to suspect that our A is going to converge too. So let's use limit comparison to find out for sure. All right, so we have our original. And then we multiply by the reciprocal of B sub n. All right. So let's see here. So you can't use a p-test? Yeah, this isn't 1 over n to a power. So we can't use the p-test on this one. All right, so I'm going to multiply through by 3 to the n and 2 to the n. So 3 to the n times 2 to the n is 6 to the n. And then I have n squared to 3 to the n. And then I'm going to multiply through here, 6 to the n minus 2 to the n. Okay, now both of these are going to infinity, but it's not immediately clear which one's going to get there faster. One thing we could do to solve this predicament here is we could factor out the largest term that we see. And the largest term that we see is 6 to the n. So I'm going to factor out a 6 to the n from everything. So if I factor out 6 to the n from 6 to the n, I get 1. And then I factor out a 6 to the n from this. All right, and then on the bottom, when I do the same thing, I end up getting this. And then once I factored out that 6 to the n from both of these here, those will just cancel out because we have 1 on the top and we have 1 on the bottom. So I effectively just divided the top and bottom by 6 to the n. All right, now we can simplify this a bit. So we have 1 plus, and then this will simplify to n squared over 2 to the n. And then this will be 1 minus 1 over 3 to the n right here. All right, now I think we're in a position where we can do this limit here. So the limit as n goes to infinity of this, well, these are just going to remain as 1s. We have n squared over 2 to the n. What's going to happen as n goes to infinity here? It's 0, that's right, because we have a polynomial divided by an exponential. So this is going to end up going to 0. And then 1 over 3 to the n, 1 is going to be 1, and 3 to the n is going to get huge. So that's also going to go to 0. So we end up with 1 over 1, which once again, we end up getting 1 for this. 1 is a very common result if you pick your BN correctly for the limit comparison test. Though remember, it doesn't need to be 1 specifically. It just needs to be something between 0 and infinity. All right, so we've done that limit now. So we can conclude, since this converged, and we would say by the geometric series test, because this is a geometric series and its value is less than 1, then we know that our original series, which was this, converges by the limit comparison test here. All right, wonderful. Now I want to do another example here. Now this time things aren't going to go as well as we would like. So let's see what happens with this. Let's say we have the sum from 2 to infinity of sine squared of n over 4n cubed minus 1. All right, and I want to try to use limit comparison for this guy here. All right, so let's see here. What do you think we should pick for Bn? Well, I think it's pretty obvious what we're going to pick on the bottom here. I think we're going to pick 4n cubed. That seems pretty good. Now, what do you guys think we're going to pick for the top? We have sine squared of n up there. What do you guys think a good thing to pick would be? Yeah, that's right. You guys are getting this. That's good. It's 1. All right. So then that leads us to believe that our original series is going to act a whole lot like, oh, this is 2, a whole lot like 1 over 4n cubed, which converges by the p-test here. All right. So then let's use limit comparison to find out for sure. So the limit as n goes to infinity of sine squared of n over 4n cubed minus 1. And then the reciprocal of this will be 4n cubed over 1. All right, so what happens is we have the limit as n goes to infinity of sine squared of n, and then we have 4n cubed divided by 4n cubed minus 1. So I'm gonna write it in that way. Could we have just picked 1 over n cubed? That would have been totally fine as well. Well, actually, we're going to see that this choice and the choice you just suggested won't actually end up working. But yeah, if this were a normal problem, we could have picked that and that would have been fine. All right, so let me ask you guys this. What's this limit going to be here? 4n cubed over 4n cubed minus 1. It's going to be 1, right? Because we have a polynomial over another polynomial, same degree, same leading coefficient. So whatever this limit is, it's the same as the limit as n goes to infinity of sine squared of n times 1, or just sine squared of n. Okay. So then what's the limit as n goes to infinity of sine squared of n? Yeah, that one's not going to have a nice answer, right? Because sine squared, that just keeps oscillating between 0 and 1, right? So that's never going to settle down to any particular value at all. So we actually get DNE for this one. And this is one of the rare times where we can't conclude something from the limit comparison test because DNE is not a number between 0 and infinity. So unfortunately, this one is not just a slanty face, it's actually a straight up frowny face. We ended up picking what we thought was a pretty good choice for BN, but it ended up not working here. So in this case, we have 2 options. So the first option is use the direct comparison test instead. And the direct comparison test would actually work for this one because, let's see. Oh, no, wait, I'm sorry. No. It goes the wrong way for this. Yeah, so direct comparison wouldn't actually be that great for this. Or 2, you could pick a different BN. So sometimes what's the quote unquote obvious BN here is a little bit different than what we see. Can you cancel out the sine squared by making it be the BN? Well, we could put it in the BN. That would cancel it out, like you said. But remember, BN needs to be a series that we can easily see the convergence of. And if we put that sine squared in there, that would make it something that we couldn't easily see what's going to happen to it. So unfortunately, we can't do that. All right, now I'm going to pick a different BN, and I'm going to pick the BN, and then I'm going to explain why I picked it afterwards. So I'm going to pick BN is 1 over n squared. So I'm going to try this as my new BN right here. All right, well, let's go ahead and try this instead. Oh, I guess we should say that the sum of 1 over n squared converges by the p-test. So notice that the bn I picked did the same thing that my original bn did right here. Yeah, what's up? Oh yeah, I said I was going to get to that in a little bit. All right. So we have the limit as n goes to infinity. So let's try this again. Let's see what happens. All right. So we have this, and I'm going to move the polynomials together just like before. Okay. Now, what is this limit going to be this time? It's going to be 0, right? Because we have a polynomial that's a lower degree on top of one with a higher degree. So this is going to 0. So this is the limit as n goes to infinity of sine squared of n times 0. And then now this is something that's nice. This will just end up equaling 0 right here. Could we use L'Hopital's rule? Not really, because it's not immediately clear if sine squared of n times n squared goes to infinity. Why would it be a suitable thing again? I haven't explained that yet. Is dne times 0, it still equals 0? It's more like something that's in between. This is always something that's in between 0 and 1, right? So if you multiply that by 0, you're going to get 0 no matter what sine's value is. So that's why this limit is going to equal 0. I never explained in the first place why I picked 1 over n squared. You guys need to pay attention. All right, so let me actually answer that question now. So let me explain why I picked 1 over n squared. I picked 1 over n squared because I knew that if I picked it to be a smaller power, then I would end up with 0 for this limit right here. All right, now let me give kind of a more general answer to that question. So for picking a different bn depends on if you want to show convergence or divergence. So what did we suspect in this problem? We suspected that this was going to converge, right? Because both of the bn's that we picked, those were converging. So if we want to show that it converges, but maybe the bn we picked wasn't working, you pick a bn that still converges, but is a bit closer to diverging. Okay, so I want to say this again because this is a little bit confusing here. I want to pick a bn that still converges, but I want it to be a little bit closer to the threshold for diverging. What do I mean by that? Well, earlier, my original bn was 1 over 4n cubed, right? And that passed the p-test by 3 being bigger than 1. But when I pick my new bn, I pick 1 over n squared, it still passes the p-test, but by not as much of a threshold. Because this time I'm doing 2 is bigger than 1. So you have to move your bn closer to the threshold of diverging, but it still needs to converge. Now, what about diverging? Well, the reasoning is going to be the same, except it's going to go the other way. Pick a bn that still diverges, but is a bit closer to converging. All right. Can you not just do this from the beginning of all these? You could do that. So like we could have picked 1 over n squared to begin with, but that's not really an obvious bn to pick from this scenario. But if you happen to kind of see in advance that this is going to happen, then yes, you could have done that originally. I'm just saying this is mostly for, all of this stuff is for if you need a non-obvious bn. Now let me explain the diverging part. So let's say our series acted, it seemed like it was going to act a lot like 1 over n to the 1/2, for example. So 1 over n to the 1/2, that diverges by the p-test because 1/2 is less than 1. So what's a series that we could pick to compare it to that would still be divergent, but would be closer to the threshold of converging? It doesn't fail the p-test by quite as much. Yeah, that's right. We could do 1 over n to the first power. That still diverges, but it's on the threshold of converging and diverging. On the exam, will you tell us what method to use or no? No, I will not tell you what method to use or which BN to use. Well, I might tell you a BN and like maybe a certain type of question, but in general, no. You guys are going to have to decide for yourself what to use. Now, that's a good point because we've been accumulating more and more of these tests, right? We have direct comparison, we have limit comparison, test for divergence, geometric series, telescopic series. We have a lot of stuff. So how do we know which one to use when? That's actually going to be our topic for next Friday. Once we learn all of the tests, I'm going to have a day where we're going to go over how we pick which one's going to be which. All right. So anyways, with all this said, let's have an example where maybe the non-obvious BN won't work, or the obvious BN might not work. There we go. It's easy to get turned around with this stuff. Determine if this series converges. And most of the time, this kind of complex situation happens because of these annoying trig functions that just oscillate. That's usually when you want to be on the lookout for this. All right, so this time we have absolute value of sine of n over 3 to the n minus n squared. So why don't we give this a try? Will this exam be the best to make educated guesses and get a good grade? It depends on what kind of educated guesses you're talking about. So oftentimes to know what to do with a series, you need to make an educated guess in the beginning as to whether it's going to converge or diverge. So that kind of educated guess is fine. I guess I would say don't do non-educated guesses where you just randomly pick an answer because there's only 2. That's probably a mistake. Actually, it's not probably a mistake. There's a 50% chance it'll be a mistake. Although I will say right now, there won't be too many of those. Most of them will still be either type in the number or have 5 answers. Which one's bigger? As long as a is bigger than 1, then a to the n will be bigger. So like 2 to the n is going to be bigger in the long run than n squared. We only have a few minutes left, so I'm just going to give you guys maybe one more minute, and then I'll go over this one. And then there's one little other thing I need to talk about, but that'll be really quick. We can't use the p-test for this one. That's right, because our dominant term is 3 to the n, so we're not going to use p-test here. Yeah, that's a good approach. You always have to use the dominant term. It's strongly recommended that you do because it's going to behave like what the dominant term does. That's why it's called dominant. So usually when we're comparing something with limit comparison, it's either, we're going to compare it usually to a P series or a geometric series. So it's typically one of those two if we're doing limit comparison. Don't worry, we'll have a day where we kind of encapsulate all of this stuff and we review it. I know it is a lot of information. Remember, pick something that's still converges, but it's a little bit closer to diverging. Those geometric series test, it's where you have something raised to the n, and you just make sure that that thing is less than 1. All right, I want to go over this one because I need to make sure we have enough time to do the last example. I don't want to keep you guys on Friday. So let's see here. I'm going to pick a Bn for this. I see an absolute value of sine of n here, so that never gets bigger than 1. So I think I'll pick 1 for that. And then between 3 to the n and negative n squared, I think 3 to the n is going to be the bigger term there. All right, so if I look at the series, which is the sum from 2 to infinity of 1/3 to the n, which is the same as that, we see that 1/3 is less than 1. So this converges by the geometric series test. So it's a geometric series. It's a number raised to the nth power, and the number being raised to the nth power has an absolute value that is less than 1. All right, so we think this is going to converge. So let's look at our limit here. So we're going to do an. So that's this over bn. And dividing by bn is the same as multiplying by the reciprocal. Okay, now let's group that stuff together and put absolute value of sine of n on its own because it's weird. So we have 3 to the n over 3 to the n minus n squared. What do you guys think this limit is going to be right here? So the dominant term on the top is 3 to the n. The dominant term on the bottom is 3 to the n. So what's going to happen with that? It's just going to be 1. That's right. But then we end up with the same problem that we had before. We have absolute value sine of n, but that can't make up its mind where it wants to be between 0 and 1. So this limit does not exist, and that's not an acceptable answer for the limit comparison test. All right, so Nick's here to the rescue. Nick says we should try 1 over 2 to the n. And why would that be a good new Bn? Well, remember my hint up here. If we think our series is going to converge, and we did earlier, then we pick a Bn that still converges. So this still converges by the geometric series test because 1/2 is also less than 1. But it's a little bit closer to diverging. This is usually the confusing part, but it's a little bit closer to diverging. So this passed the geometric series test because 1/3 was less than 1. There's a 2/3 gap between these. 1/2 still passed because it's less than 1, but there's only a 1/2 gap here. So it's actually a little bit closer to failing the test. So the difference between passing a test with like a 90 or passing the test with like an 80. This passed the test with a 90, but this one passed with an 80. They both still passed, but this one did it better. So we want to pick one that did actually a little bit worse there. So it's closer to 1. All right, so let's try this now. We have absolute value of sine of n over 3 to the n minus n squared. And then we're going to divide by 1 over 2 to the n, which is the same thing as doing this. All right, so if we do the same method as before, so our dominant term on the bottom is 3 to the n, and our dominant term on the top is 2 to the n. What do you guys think is going to happen with this limit here, since the top one is weaker? It's going to go to 0. That's right. So we end up getting 0 for this. And remember, if we're trying to show convergence, 0 is actually okay for this. Remember, that was one of the other conditions we had earlier. Where's that paper? Oh, here it is. Yeah, so remember, if we want to show convergence, 0 is actually an acceptable value. If we get a limit of 0 and the comparison converges, then the whole thing converges as well. So 0 is actually okay to get here. All right, so that's more practice with a non-obvious Bn. Okay, now I want to go over one more thing. How do we get 0 again? It's because this limit is 0 here. We have 2 to the n over 3 to the n. 2 to the n is a weaker function than 3 to the n is. All right, now I want to talk about one more thing, and then you guys can have a wonderful weekend. So in this one, I want to take a look at this function, or this series. Sine of 1 over n squared. Now, this one kind of defies most of what we've done so far because there's not a fraction at all. It's just sine of something. Okay, well, what's going on with this? So here's the rule if we ever have a trig function of 1 over n to a power. So if we ever have a trig function of 1 over n to a power, we compare it with the following. So if we have sine of 1 over n to a power, we're going to compare that with just 1 over n to the power. If we have tangent of 1 over n to a power, we're going to compare with the same thing, 1 over n to a power. But if we have cosine of 1 over n to a power, we compare that with 1. And then with the other trig functions, you just take the reciprocal of whatever these were. So anyways, so for sine of 1 over n squared, my bn here, according to this formula, well, if I have sine of 1 over n squared, I should compare it with 1 over n squared. Okay, and how is this going to work? This isn't even a trig function at all. This seems kind of strange, but trust me, it'll end up working out here. So if we look at what this does, 1 over n squared, this converges by the p-test. So we think that this will probably converge too. So let's use our limit comparison test. So we have sine of 1 over n squared divided by 1 over n squared. All right, now let's see here. If we want to figure out this limit, let's send n to infinity and see what happens. So if we send n to infinity, we have sine of 0, it looks like. Sine of 0 is 0. If we send n to infinity on the bottom here, we also get 0. So what does that mean that we can do? We can do L'Hopital's rule. That's right. So when we do that, we have cosine, the derivative of sine, 1 over n squared, times the derivative of my inside, which will be negative 2 over n cubed if I do the power rule there. And then here I'm just doing the derivative of 1 over n squared alone. So that'll be negative 2 over n cubed. And lo and behold, we have the same thing on the top and bottom. So those will cancel out. Now, if we send n to infinity here, we have 1 over something going to infinity. That will be 0. We have cosine of 0 is 1. All right, so then that means that this series converges by the limit comparison test. And why were you allowed to use L'Hopital's rule again? Because it's a 0 over 0 limit. If we send n to infinity here, we have sine of 0 is 0. We send n to infinity here, we just have 0 on the bottom. So it's 0 over 0. All right, so the moral of the story is this chart. If you ever see sine, tangent, or cosine of 1 over n to a power in one of your problems, just imagine it as being 1 over n to the power for sine and tangent, or just as a 1 for cosine. So that's kind of what I was trying to get at here. All right, that is it for today. Sorry, I went a few minutes over here. Next time we will be looking at another series test. So I will see you guys on Monday.